Welcome, ladies and gentlemen. This is section 2.4 of Miss Quinn's Geometry. We're talking about the properties of good definitions today. Property number 1. Good definitions only include words commonly understood and used, defined earlier, or purposefully undefined. Please remember that in geometry we have a few words that are designated undefined. Property number 2. Good definitions accurately describe the idea being defined. And number 3, they aren't lengthy or too long. They include no more information than is absolutely necessary. So they're not wordy. All right, let's look at the example of the definition of a midpoint. Midpoint of a segment is the point M on AB where the length of AM equals the length of MB. This is very specific. I can see that this segment, AM, its length is equal to this segment, MB. And that is the definition of a midpoint. Now, if I know K is the midpoint of CD, let's draw a picture of that scenario. I have some segment CD where C and D are my endpoints, and K is smack dab in the middle. If I know the length between C and K is 6, let me write that in a different color so you can see that. So length is 6. Then what length would KD have? Hopefully you'll agree with me that they have to be the same due to the definition of a midpoint. The midpoint we just found, KC has to equal KD. So they will both be 6. Thus, the entire length is going to equal 2 times 6, or 6 plus 6, which would be 12. And so we can see that CD, the entire length, equals 2 times half. 2 times KD. All right, let's work with some example problems. If M is the midpoint of AB, I have some line segment AB with a midpoint at M, and I know that the distance between A and M is 2x plus 1, and I know that the distance between M and B is 4x plus a negative 13. Now when we're adding a negative, wouldn't you agree that we're actually subtracting? Now if I want to find AB, the entire length, first I'm going to need to find the value for x, find the value of one of these half lengths, and then multiply that value by 2. So to find x, if I know that these two lengths are equal to each other, let's go ahead and write an equation where we set them equal. So I have 2x plus 1 equals 4x minus 13. To solve for x, I'm going to subtract 2x on both sides. I'm going to add 13 on both sides. And I'm going to divide by 2. And x equals 7. Now that I found x, let's go ahead and find AM. If AM equals 2x plus 1, I would get 2 times 7 plus 1. Does everybody agree that that's going to be 15? Thus, AM equals 15. Now, remember, my original goal was to find AB. And that entire length would be what? Hopefully you'll agree it's 2 times 15, which equals 30. My final answer is 30. All right, look at number 2. CD equals 70, and K is the midpoint. I always like to draw a picture. Here's my gorgeous line segment, CD. K is smack dab in the middle. Now I know the entire length and I know the value of KD. Now we learned earlier that I could take 2 times the value of 1/2 of the line and set it equal to the length of the entire line. Hopefully that makes sense. If I know that this half, I could multiply it by 2 and set it equal to the entire length. So that's exactly what I'm going to do. I'm going to say 2 times 7y plus 20 equals 70. And I'm going to divide both sides by 2, and I get 7y plus 20 equals 35. Now I'm going to subtract 20 on both sides, and I get 15. When I divide by 7, I get 2 and 1/7. And that was what I was looking to solve for. Excellent. Let's move on. Let's look at the definition of a circle. A circle is a set of all points in a plane at a certain distance. Its radius from a certain point. Its center. So basically, every single point on this outside is equidistant from the center. That's the definition of a circle. We have a biconditional statement that we need to learn about today. And that means if A implies B and B implies A, then we can say it is biconditional. It goes in both directions. We often say if and only if. For example, another way of writing A biconditional B is A if and only if B. Now, if and only if, evidently it's too long for some people to write, so a lot of times we use IFF. That means A if and only if B, if you see IFF. Or we might call it if. So let's do some definitions as biconditionals. Point M is a midpoint on segment AB, if and only if M is the segment AB, and AM equals MB. So basically, I took the definition of a midpoint and I rewrote it as a biconditional. That means M is a segment on AB and AM equals MB, if and only if the point M is a midpoint on the segment. It goes in both directions. You can write either one first. Let's practice doing that yourself. Write the definition of parallel lines as a biconditional. The definition of parallel lines are two coplanar lines which have no points in common or are identical. So I might say, do you have any ideas? I would say parallel lines. No, that won't work. How about lines are parallel? That sounds nice. Lines are parallel. If and only if. Let's write if. Lines are parallel if and only if the lines are coplanar, have no endpoints or no points in common, or are identical. All right, so you could write it either way. Lines that are coplanar and have no points in common or are identical if and only if the lines are parallel. I think I like the way I wrote it better. All right, you have an assignment for tomorrow. For tomorrow, I would like you to decide which properties, 1, 2, or 3, show that A, B, and C are not good definitions. I will see you tomorrow.